Hi, welcome to our 22nd lecture of our graduate combinatorics course. So today we'll continue discussing a little bit about Eulerian graphs and some applications of this theorem of Euler and Hierholzer. And then we'll move on to talk about bipartite graphs. So let's start with Eulerian graphs. So as you recall, last time we proved this theorem that states that if gamma is a connected graph, then gamma is Eulerian even only if the degree of every vertex is even. And as you may recall, we have this definition that gamma is called Eulerian if it contains a closed trail that contains each edge of gamma. So each edge, it's contained once, because in the trails we're not allowed to repeat edges. And closed means that we start at the same vertex where we end up. So we start at vertex X and we go through every edge exactly once and return to vertex X. Now, what if we don't want to have, so what if we have a situation in which maybe we want to start at a vertex, go through every edge exactly once and end up at a different vertex. So let's state this as a corollary. We'll see it, we can figure out the situation from the Euler-Hierholzer theorem. So let's be in the same scenario as before. Let gamma be a connected graph. And let's take two vertices at X, different from Y, be two vertices of gamma. And we can say that the graph gamma contains, let's call it XY Eulerian trail. Well, let's call it a XY trail that contains each edge. Yeah, it's better with Eulerian trail. I'll give the definition in a second. So let's say that the graph gamma contains an XY Eulerian trail if and only if the condition is that the degree of X and the degree of Y are odd and degree of Z is even for any Z which is not X and is not Y. So in order to have a trail from X to Y that goes through every edge exactly once, a necessary condition is that the degree of X to be odd and the degree of Y to be odd and all the other degrees to be even. And this can be seen easily by applying a similar argument to the one we did at the beginning with the bridges of Königsberg and so on. And we'll prove in a second that this is also sufficient for the existence of this trail. So let me just give you this definition here. So by an XY Eulerian trail, it's a trail that starts at X, ends at Y, and contains each edge of gamma. Okay. So to prove this theorem, so like we said, we just have to do the. I mean, in some sense, this theorem is actually, this corollary is equivalent to Euler-Hierholzer theorem. And here's how the equivalence works. So let's say here we have this graph gamma, and I have here the vertex X, which has an odd degree, and I have here the vertex Y, also with an odd degree. Now, what I can do from X, from gamma, I can construct a graph, or technically it's a multigraph, gamma prime, in which I keep everything as in gamma. So, except one thing, I add one thing, namely, I add one edge from x to y. Now, if there was an edge already between x and y, then now will be there will be multiple edges between x and y. So the graph wouldn't be simple. But if there were, in the graph gamma, if there was no edge between x and y, now this graph would still be simple if gamma was simple. So now what happens is that yeah, it's not too difficult to see that if we have our hypothesis of d of x and d of y odd and d of z even for any other z, this is equivalent in the graph gamma prime that d of x here and d of y here are even, and also d of z is even. Those degrees don't change. So in the graph gamma prime, we are going to have we will have an Eulerian circuit, and we can arrange that Eulerian circuit such that it starts at x and it ends up at y, and we can arrange it such that this edge that we added, it's only used at the end when you want to loop back from y to x. And so if we remove that edge, you get an xy Eulerian trail, and so on. So that's essentially the argument, the easiest way that you can see this result. And like I said, you can actually observe that these two results are in some sense equivalent. If you get the theorem, you can get the corollary, and I think vice versa, you can also prove it. Okay, so now you can play this game if you want. There's an app on the phone, which is called One Touch app, in which you're given, a graph. So I'll give you an example here, and you're asked to draw it in one touch with one pen stroke, essentially. So let me give you a fairly complicated graph. Here. This way. Okay. So here the question is, can you draw this figure going through every? So you start at the vertex, go through every edge exactly once, and possibly end up with a different vertex. So you can play this game with pretty much any figure. So let's start with a complete graph. So a graph on n vertices where you have edges between any two. You have an edge between any two distinct vertices. So if I have, let's say, n equals 3, I have, these are my my 3 vertices. I can call them, let's call them, for some reason, I'll call them 0, 1, and 2. And you can draw it with one stroke by starting at 0, go to 1, go to 1, and then go to 2, and then go to. So that works. He has a Eulerian circuit. When you go to n equals 4, and you have this graph, this is not going to work. So no matter how you try to draw it, you can do this way, this way, this way. You get an Eulerian trail between, let's say, in this case, vertex 0 and vertex 1, but you are not going to get an Eulerian cycle, and that's a circuit, and that's because of, it's, I guess, common sense and Euler-Hierholzer theorem, because the degrees in this graph here on 4 vertices are actually all odd. So you could draw all of it with 2 pen strokes if you want, because you have 4 odd degrees, and you can pair them up, and you can do that. So I'll leave it as an exercise for you to figure out this graph here, if you can draw it, and you can play more with this One Touch app if you want. Let me give you one application of this silly games of drawing that we're talking about here. And that is in the realm of dominoes. So dominoes are these rectangles that have a number on one side and a number on the other. Sometimes the space is left blank, so it is possible that you know, one of the x, if it's blank, we can think of it as a zero. And there are various domino games. So let's start with perhaps the simplest, in which the pieces are so I have x and y between 0 and 5. And we have how many pairs and how many doubles? Well, if x is different from y, then we have 5 choose 2. So that's 10 pairs. And if x equals y, then we have 5 choose 1. Well, 0, 1, 2, 4, I'm sorry. And in this case, we have 5 doubles. And a natural question is, can we actually lay down these 15 domino pieces in a circular shape or in a line shape, such that the number that's the end of one domino piece equals a number that's the beginning of the next domino piece. So let me give you an example of such arrangement. So again, 0 stands for blank, so you could do 0, 1, and then you can do 1, 3. So you see here the 1 and the 1 are the same. Then you can have 3, 0, 0, 2, 2, 3, 3, 4, and something that starts with 4, 4, 1, 1, 2. Let me put it this way, 2, 4, and then 4, 0. So these are all the pairs. And now what do I do with the doubles? Well, for the doubles, I have various possibilities, so I can insert them. So this gives me actually a circular arrangement, because you can see that the 0, 1 with the 4, 0 here, they also satisfy this property. You have 0 at the place where they meet. Now, I could, if I have a piece of, let's say, if I have a piece which is a 1 and a 1, that one I can insert it whatever, either here, or I can actually insert it over here. So you have actually two possibilities where you can insert it. And similarly for any other piece that has a double. So if you have a 0, 0, that could go here, or it could go here between 1, 0 and 4, 0. Okay. So how do you model this, or how do you study this problem with? So I mean, what is the problem? One question is, can you always find? You know, how did I come up with this this domino arrangement in a circular fashion? And it has something to do with Eulerian circuits. So let's think about the complete graph on 5 vertices, and let's label the vertices 0, 1, 2, 3, 4. And what I wrote there is essentially an Eulerian, it's an Eulerian circuit. So 0, 1, 1, 3. So it means I start at 0, I go 0, 1, I go 1, 3, and then I go back to 3, 0. And I basically, what I did is I wrote in blue the edges that I traversed on this Eulerian circuit. Now this graph, so this graph is K5. Each vertex has degree 4, so therefore the graph is called 4 regular, and 4 is even. So that implies that K5 is Eulerian. So there is a way to draw it. So if I have the vertices me just put the vertices here, label them 0, 1, 2, 3, 4. What I did was I started at 0, go to 1, go to 3, go to 3, go back at 0, and then I went 0, 2, 2, 3, 3, 4, 4, 1, 1, 2, 2, 4, and 4, 0. So that's one example of an Eulerian circuit, and that gave generated this arrangement of domino pieces. You can think of these doubles as actually having one loop at each vertex in some sense. You can think of having a loop at each vertex, but because of our assumption that the loop contributes 2 to the degree of the vertex, this new graph with loops is 6 regular. So it also has an Eulerian circuit. So either way, I hope that this convinces you that you can have an arrangement of these domino pieces. Now, how many arrangements? How can you actually count them? And I posted on the Google Drive. I posted a paper by Mackay and Robinson in which I actually do computation of these Eulerian circuits in complete graphs on n vertices with n odd. And so two Eulerian circuits are considered to be the same if one is a circular permutation of the other. So for example, let's do when n equals 3, if I just draw the graph 0 with 3 vertices, the complete graph, this has 2 Eulerian circuits with this assumption. One Eulerian circuit is 0, 1, 2, 0. So here there are no multiple edges, so we can just give a list of the vertices that we traverse. And this is considered to be the same as 1, 2, 0, 1, and it's the same thing as 2, 0, 1, 2. So all the circular permutations in counterclockwise fashion. And then you can write down the clockwise one. So 0, 2, 0, 2, 1, 0, 2, 1, 0, 2, or 1, 0, 2, 1. So there are 2 of them. So that's easy for n equals 3. Well, how many are going to be for n equals 5? So this is our question about the number of possible domino arrangements. So if we have this graph 0, 1, 2, 3, 4. And this question was studied more than 100 years ago by a French mathematician by name Gaston Tari. And you can find this description in a very nice book, which is called Mathematical Recreations and Essays. Written by Walter William Rouse Ball. And then the newer edition is with Harold Scott MacDonald Coxeter. These are some famous mathematicians. And in this, so we'll talk about Gaston Tari. So Tari, I look it up, between 1843 and 1913. We'll talk about him later on when we talk about Latin squares, 6x6 Latin square and so on. And he talked about these figures. He called this figure, the term that he used was unicursal figure. So one of these figures that you can write with one pen stroke from one vertex to the other. And also the problem that was studied was the number of these domino arrangements. So there, like I said, 2 possible situations in which you want cyclic arrangements or line arrangements. In cyclic arrangements, all circular permutations are considered essentially the same. So in our previous figure here, I could have started at 0, 2 and gone around these dominoes in the circular fashion this way, and that's considered to be the same arrangement as the one that I just drew. Okay. So now the way one can figure this out, I won't go into all details, but I'll just give you the basic ideas for the. So if we have, let's say here, a number of A cyclic arrangements, then over here, I will, no, A will be so the number will be, A would, if A is a number of these Eulerian circuits in Kn. So things like this blue arrangement that we drew here. Then in this situation, when n equals 5, so we're looking at K5, the number of cyclic arrangements of dominoes where you now insert the 5 pairs would be, so this number would be A times. Now for each piece that is a pair, there are two positions where it can be inserted. So you have 5 pairs, so it would be 2 to the 5 times A. And so that's how many cyclic arrangements you have. And line arrangements, you can just basically cut any of these cyclic arrangements and just put everything on the table as a line. But you have 15 pieces, so there are 15 places where you can cut, times 2 to the 5 times A line arrangement. So the problem reduces to counting Eulerian circuits in the complete graph on n vertices where n is odd. Like I said, you can find the details about general n and asymptotics in the paper by Mackay and Robinson. Here, let me give you a quick idea. How would you count them for let's say n equals 5? So what you do then, you count here, you kind of reduce the problem to, it's a recursive procedure. You reduce the count from a graph on 5 vertices to a graph or a multigraph on a smaller number of vertices. So here, when we're counting these Eulerian circuits, we can assume that they start at 0, and then you can split them according to which edge is incident to 0, pair up in the first pass, that returns back to 0. So you can say if 0, 1 and 0, 2 are coupled, so in such a pair, then it means that 0, 3 and 0, 4 are coupled in the second part. So maybe it's easier to explain it here. In this situation, 0, 1 and 0, 3 are coupled because you start at 0, 1 on the first part, and you come back on 0, 3 or 3, 0. And then 0, 2 and 0, 4 are coupled. Okay, so that's how it works here. So in that situation, then the number, you can work out that you can eliminate 0, and 0, 1 and 0, 2 are coupled. The number of Eulerian circuits of that form is the same as the number of Eulerian circuits in this multigraph, where the 0, 1 and the 0, 2 become, you can think of 0 as being a point there on 1 and 2. And so you have this multigraph where you have two multiple edges between 1 and 2 and 3 and 4. And similarly, if you have, in the second case, if you have 0, 1 and 0, 3 coupled, and 0, 2 and 0, 4 are coupled. So in this situation, the number is the same as the number of Eulerian circuits in this graph. And finally, if we have 0, 1 and 0, 4 coupled, then 0, 2 and 0, 3 are coupled. And then you get this figure. Like this. And then you can reduce the problem further from these graphs. I mean, they're all the same, these three ones. So it's enough to calculate the number for one of them. And I think in the end you can end up with this A being equal to 264. And so the number of each of these other ones, like if we call this number B, then it's clear that this number is also B. This is also B because all these graphs are isomorphic. And so you have A equals 3 times B, and B is something like 88, I think. So yeah, how do you calculate? You keep doing this procedure of suppressing or removing a vertex and reducing the problem to a smaller graph until you get to something of this form, either something with loops or in this situation, something of this form where you have either 2 edges or 4 edges or something like this. Okay, so let's say if I have here some, I'll put here just some vertex label. Let's call here 3 and 4. Let's call them 3, 4, and 3, 4. Then how many Eulerian circuits we have for this graph? Well, you have 2 edges there, and you can give them names. You can call the edge on the top F, and the one below it G. So you can do 3F, 4, and G3. And you can also, this is the same thing. If you permute it in circular, it's the same thing as 4G3, F4. But you can get another one, which is 3G4, F3, which is the same thing as 4F3, G4. So in this case, the number A is 2 for this multigraph. How much is here, like for 3 and 4, or so this case, this problem is more generally if you have, for example, something like 2k edges between these 2 vertices, let's still call them 3 and 4, then what's the number of Eulerian circuits? Well, you can start at either 3 or 4, so that will give you 2 choices. And then you can pick these edges, and it's a permutation of 2k edges, so it's 2k factorial, but they're circular permutations. So you have to divide by 2k because each circular permutation is equivalent to 2k of this circular permutation as itself. So the number is 2 times 2k minus 1 factorial. So for this one here, A would be 2 times 3 would be 6. And I leave it to you as an exercise how many would be for over here. Anyway, so that's basically the idea of how you can reduce this problem from larger graph to smaller graphs. And the calculation gets even more complicated. I mean, here you can do it by hand, but the calculation can get more complicated for the other domino pieces. So the kind of perhaps more familiar set of dominoes has all these numbers. So let's say we have 0, 1, 2, 3, 4, 5, 6. And so on. And here the pieces are of the form xy, and you have x and y between 0 and 6. And if x is different from y, then we have 7 choose 2, which is 21 pairs. And when x equals y, we have 7 choose 1, which is exactly 7 doubles. So here, one ends up with 28 dominoes. And by an argument similar to the previous one, you can show that there is a circular arrangement of all these dominoes, and you can actually count them, but I'm not going to do that. Okay. So let's move now to another class of graphs, which are called bipartite graphs, where again some notion of parity will come into play. So let's start with an example. Let's say we have the following situation. We have a collection of workers, which I denote here by these dots. So work 1, 2, 3, 4, 5. And we have some jobs. Job 1, job 2, job 5. And now some workers are qualified to do some jobs. So for example, worker 1 is qualified to do job 1 and qualified to do job 3. So we represent this by a graph. Worker 2 is qualified to do job 1 and also job 3. Worker 3 can do job 2, job 4, and job 5. Worker 4 can do job 1 and job 4. And worker 5 can do job 3 and job 4. Anyway, the number doesn't have to be equal, but I chose this for simplicity. And the question is, can you can ask it from both ends. You can ask, is there an assignment of one job per worker such that no two jobs are the same, and each worker gets a job that is qualified or she is qualified to do. So you can ask, you can give job 1 to worker 1. So in that case, job 1 cannot be given to worker 2 or worker 4. So then you can say, okay, worker 3 gets job 2, maybe worker 2 gets job 3, worker 5 gets job 4, but we don't get any job for worker 4, and it's the same thing for job 5. So we'll see later in this course how this problem can be solved using what is called Hall's marriage theorem. So we'll give a necessary and sufficient condition for the existence of such an assignment. This is called a matching. This situation, a perfect matching. But before that, let's get more familiar to this type of graph that we encounter here, where you see you have these two type of vertices. You have these vertices on the left, and you have these vertices on the right. And the edges that you have just have one endpoint in one set. Let's call this maybe W, and another endpoint in the other set. Let's call it J. So such a graph is called bipartite graph. And another way of looking at it is that the vertex set is split into two parts, W and J. And in general, these two parts, W and J, do not have to have the same cardinality, such that there are no edges inside W and there are no edges inside J. So let's start with this definition. So let's say we have gamma, and we will restrict ourselves to simple graphs. So no loops, no multiple edges, with vertex F, V, and E. And now, if we have a subset S of vertices, is called independent, or sometimes the name stable is used. It's also called stable. If for any x and y in S, x is not adjacent to y. So I'll use this this notation. I guess maybe I didn't. I will use x tilde y. That means that x and y are adjacent. There is an edge between them, and x not tilde. That means x and y are not adjacent. Okay, so that's what it means that S is an independent set or a stable set. And a parameter that's of interest in graph theory, we denote it by alpha of gamma, is the largest cardinality of an independent set in gamma. This is called the independence number of gamma. And we'll return to it because it's quite an important parameter in a graph. Okay, but for now, so in our situation, W is an independent set and J is an independent set, but also, you know, W1 and the set W1 with J2, there are no edges there, so that's also an independent set. And also a single vertex is an independent set because we don't have loops in this situation. Now, what is a bipartite graph? So the graph gamma is called bipartite. I guess if gamma consists of either consists of a single vertex, let's consider that bipartite, or there is a partition of its vertex set into two independent sets. So gamma single vertex, so just one vertex, we consider that, yes, is this a single vertex bipartite graph? Oh, let's just scrape that, don't worry about that. So we'll look for n greater or equal to 2, so we have at least 2 vertices. So we'll use this definition that the graph is bipartite if there's a partition of its vertex set into 2 independent sets. So we could have 2 vertices on one side and 1 on the other. So this graph is a bipartite. You could have this situation. This graph is bipartite. You see the partitions. This is the partition, and each of those 2 parts have no edges in them, so on. You can have a bunch of isolated vertices, and you can that's in that situation. You see the partition is not unique. You can partition this vertex set with 5 isolated vertices into many in many ways into 2 independent sets and so on. Okay. Now, okay, just one more definition. So a complete bipartite graph, so gamma is a complete bipartite graph. Well, before we get to this one, so here, these 2 independent sets, sometimes they're called partite sets. Partite, there's a more general notion than than bipartite graphs. You can talk about 3-partite, 4-partite, and so on, and the definition is similar. A graph is called 3-partite if its vertex set can be partitioned into 3 independent sets, and so on. So that's why these sets are called sometimes partite sets, or sometimes are called color classes. And they're called color classes because from coloring the graphs, one important problem is you want to give each vertex of a graph a color such that no two adjacent vertices get the same color. So in that situation, you can, for example, you can color these vertices on the left here. You can color each of these vertex red, and you can color each of these vertex on the right blue. So the set of red vertices, it's this left side of the least independent set, and similarly the other one is the set of blue vertices. So here you can color these ones with red, and you can color these ones with blue, and this is what is called a proper coloring. So every edge that has the endpoints have different colors. Okay, so I will refer to them partite sets or color classes. Okay. Now, so what can you say about bipartite graphs? How can we characterize them? So let's look at some more examples. So let's say we have R vertices here to the left, and let's say we have S vertices to the right. In my case, R is 4 and S is 3, and we put all the edges between them. So we have R times S edges and R plus S vertices. This graph, it's denoted by KRS, K, capital K, R, comma, S as a subscript. This is the complete bipartite graph with partite sets or color classes of sizes R, R and S respectively. And it's the analogous of, I mean, I guess I haven't defined it until now, the K, let's say if I have here n vertices and I put all the edges between any two pairs, Kn, it's called a complete graph on n vertices. So the complete graph on n vertices is bipartite only when n equals 2. Now, so there are many bipartite graphs. What's common amongst all of them? Well, if we try to do something as before, you know, walk on every edge exactly once and try to come back to where we started. Well, this graph KRS is definitely not Eulerian because the vertices on the left have degree 3, so that's not going to work. But we notice one thing, that when we do a cycle, when we traverse a cycle, let's say you start on the left, every time you make a move, you go on an edge, you move from one partite set to the other. So if you were to start on the vertex on the left and come back to that vertex after some number of steps, that number of steps that you take has to be even, because that's the only way that you can come back. Now, of course, that's so that's a necessary condition. But it turns out that that's also sufficient, and this is a famous theorem in graph theory, which was due to a Hungarian mathematician named Dennis Konig, who wrote one of the first books on graph theory. And so let's prove it here. And it suffices to restrict ourselves. It's to connect the graphs. So let gamma be a connected graph. Let's say on n greater or equal to 2 vertices. The graph, so what we'll prove is that the graph gamma is bipartite if and only if it contains no odd cycles. We'll see that this is a very useful characterization. proof. So let's go from left to right. So assume that gamma is bipartite with partite sets. Let's give them some name, X and Y. Okay. Now any closed walk, not just any cycle, but any closed walk in gamma must have an even number of edges. Because again, you have this picture, this is X, this is Y. If you start with a vertex here, let's call it A, you want to come back to X, you have to do a multiple of 2 steps. Okay, every time. So the only way you can come back to A is after an even number of steps. So that's the property of any closed walk, not just a cycle. So that means that thus any cycle, if it exists, any cycle of gamma, if it exists, must be even, must have even length. Okay. So let's quickly go to the other argument. So now let gamma be a graph that is that is connected and has no odd cycles. I would like to prove that it's bipartite. So how do we go about it? We take a vertex, let's let A be a vertex of gamma. Okay, so gamma is vertex V and I set E. And now, so this is A. It has some neighbors. Those neighbors have some neighbors. So it could go some like that in general. And the neighbors have some neighbors and so on. So you have this picture of a graph. So now what happened? The graph is connected. So that means that for any B in V, there is an A-B path. There is a path from A to B. Even in the case of B equals A, that path is just one vertex, so on. And so for we can define by f of B, oh, let's call it L of B. L of B is the shortest length of an A-B path. So you look and see how fast you can get from A to B and count the number of edges and take the smallest such number. So here's how it is. In this situation, the vertex A, L of it is 0 because you don't do any steps and you're there. All these vertices here have L of them equals 1. All these vertices here have the value of L equals 2 and so on. This is it's called the distance between A and B, essentially, 3 and so on, okay? And now you see some of these numbers are even, some of them are odd, and that's going to give us the idea to split the vertices according to which ones are even and which ones are odd. So let's call X to be consisting of all the vertices B, of the property that LB is even. So in this situation, it's A, and this vertex is here. And let's do y. The vertices, let's call them c, such that LC is odd. And in our situation, you have the vertices distance 1 and distance 3. And I'm a bit out of time here, but the idea is now to prove that x and y are independent sets and that are partition the vertex set. And that will prove that the graph is bipartite. Now, one part is very easy, the fact that x and y partition the vertex set of gamma. And why is that? Well, from their definition, in x we put the vertices with where this function L is even, and in y we put the ones where this function is odd. So it's clearly that it's obvious that x intersect y is the empty set. And then the other fact is that, because here we have even, and here we have the ones that L is odd. So LB is even, and here LC is odd. And now, because the graph is connected, every vertex is B is on one of these. There is some AB path, and there will be a shortest length of such a path, and that could be either be even or odd. There's no other choice. So that implies that X union Y is V. So that's easy. The trickier part is X and Y are independent sets. So X and Y are independent sets. And this follows from the following. So I'll just quickly go through it. If you have, so let's just show that X is independent sets. So in X we have A, and we have these vertices at, LB equals 2, and LB equals 4, and so on. LB equals 6, and so on. Now, there's no way you can have so what we planning to show is that there are no edges between these vertices in blue. Now, one thing is that you cannot have an edge, for example, from A to LB, because such an edge would imply that for that vertex, the other vertex containing an edge, that vertex would have the L value equal to 1 because it would be adjacent. So that would be a contradiction. Similarly, if I have an edge here between 2 and 4, then what do I have? I have a path from A to B that has two edges on it, and with that edge, that will give me a path to this vertex here of length 3, but that vertex has the L value equal to 4. So that edge cannot exist either, okay? Now, where could we have another edge? Perhaps we could have an edge here at this level. So in that situation, we have a way of reaching this vertex B here by a path of length 4, even in general. And perhaps there is another way of reaching this other vertex here, C, also by a path of length 4. So if we combine these two paths and the edge BC, so we take the path from A to B that has length LB, and then we take the edge BC, and then we go from C back all the way to A using this path from A to C of length LC. What we end up with a closed odd walk. And we will prove, and this is in the textbook, and please read it before Wednesday, that every closed odd walk contains an odd cycle. But that's a contradiction, because our hypothesis is that the graph doesn't have any odd cycles, and therefore this proves that X is an independent set, and similarly Y is an independent set.